In this video, we're looking at limits at infinity. Now, limits at infinity, by rule, are just horizontal asymptotes of a function. So when we define them, the line y equals L is a horizontal asymptote when the limit as x approaches negative infinity is L, or the limit as x approaches positive infinity of the function is equal to L. So the line y equals L is the horizontal asymptote. Now, limits at infinity have many of the same properties of the limits discussed earlier, in chapter 1. The main ones being that if the limit of f exists and the limit of g exists, then the limit of the sum is just the sum of the limits. The limit of the product is just the product of the limits, okay? And these hold true not just for x approaching infinity, but also for x approaching negative infinity. So for rational functions, the rules are the same for infinite limits as the rules for horizontal asymptotes are from pre-cal because, well, they're the exact same thing. First thing is, if the power of the numerator is higher than the power of the denominator, there's no asymptote. What this means is that as x approaches infinity, we're getting either positive infinity or negative infinity based on whatever the sign is. If we're not approaching some number, we must be going up unbounded or going down unbounded, right? One of the two. So if the power of the numerator is less than the power of the denominator, then the asymptote is 0. Thus, the limit as x approaches infinity is also 0. If the power of the numerator and the denominator are equal, then the asymptote is just the ratio of the leading coefficients of the numerator and the denominator. Thus, the limit as x approaches infinity would be the ratio of the leading coefficient of the numerator and the leading coefficient of the denominator. So this leads us to a following theorem because of that second rule, this one right here, okay? And that tells us that if we take the limit as x approaches infinity of some constant divided by x to a power, doesn't matter what the power is as long as it's a positive rational number, then the limit's 0. Because all it's saying is x is getting really, really big. And any number divided by an infinitely big number is going to approach 0. And it doesn't matter whether we're going positive or negative. We're still approaching 0. Now, for functions that aren't rational, and these are particularly those that have radicals in them, then we have to use another method, okay? We can't just look at them because all of those rules only apply to rational expressions. So if the function has a radical on the top or bottom, what we have to do is divide both the top and the bottom by the variable that has the greatest power in the function, okay? However, we need to make sure to write the variable in radical notation. Now, for square roots, or if the radical is even, there has to be two different things that we do. We have to let x be the positive square root, and we have to let x be the negative square root. So I'm going to explain a few things real quick. Divide by the variable with the greatest power. So what if I had the square root of x squared over x? What's the greatest power here? If you said x squared, you got to be careful because this is the square root of x squared. What's the square root of x squared? Square root of x squared is x, right? So really, this is equivalent to just x, so x and x. So the highest power is just going to be x to the first. Same thing if we had x squared over the square root of x to the fourth. What's the highest power? Well, it's x squared, right? However, if we do use x squared, we have to make sure and write the variable in radical notation. So if I want x squared, isn't that the square root of x to the fourth? Right? Isn't those the same thing? So we're always going to square this and then take the square root, remembering to use plus or minus if we're dealing with a square root. Now, how does that look in practice? 3x minus 2 divided by the square root of 2x squared plus 1. So the highest power is x to the first. So I need to divide everything by x. But I know that x is equal to the square root of x squared. We have to write it in radical notation. And since the square root is positive or negative, and this only means the positive version, we also need to do negative square root of x squared. So I'm going to divide every piece of this by x. So this is the limit as x approaches infinity of 3x over x minus 2 over x. And this is square root of 2x squared plus 1 divided by square root of x squared. So this gives me the limit as x approaches infinity. 3x over x is just 3 minus 2 over x divided by, what do we have here? We can rewrite this as one simple radical, 2x squared plus 1 over x squared. We're going to separate that into separate and say that this is 3 minus 2 over x over, this is going to be square root of 2 plus 1 over x squared. So now, at this point, a while ago when we try to plug infinity in, you get 3 times infinity minus 2, square root of 2 times infinity plus 1. This is just infinity over infinity. That's called an indeterminate form, nothing we can do. But here, if we plug in infinity, what's 2 over infinity? That's 0, right? That goes to 0. Plug it in here, that goes to 0, and we're just left with 3 over the square root of 2. That's the limit as x approaches infinity. If we wanted to know about the limit as x approaches negative infinity, we would need to use negative square root of x squared. So this is going to give us the limit as x approaches infinity of 3x over x minus 2 over x divided by the square root of 2x squared plus 1 over negative square root of x squared. The only thing different here is that minus sign. So it's going to work out exactly the same. You're going to wind up with negative 3 over root 2. So notice they have different horizontal asymptotes depending on which side they're going to. That's a byproduct of this irrational type of function. Rational functions always have the same horizontal asymptote on both sides. So you'll notice that with these radicals, you'll wind up sometimes with different ones. Now, I want to explain something real quick. This notation when we use negative infinity. Now notice we used negative square root of x squared down here, but we didn't use negative x down here. Why? Because this is the case for, this is when x is positive, this is when x is negative. Now, I can't plug a negative value in here because that square will eat it, right? If you get a squared number, the minus sign goes away. I have to tack that minus sign on the outside to denote that this x value is indeed negative, okay? The same thing, really, what you can look at this as being as x equals square root of x squared because x is greater than 0. But if x is less than 0, we still have this, but we're going to move that minus sign. We're going to divide by negative 1. We get x equals negative square root of x squared. That's why the bottom is negative, but the top is not. The top is just x. If x is negative, the negative sign is there. Down here, if x is negative, it gets eaten, so we have to kind of add it on there. All right, so that's the more complicated kind, the ones that involve radicals. Let's go back to some more basic ones. What do we have here? The limit as x approaches infinity of x cubed. Well, this is over 1, right? Or over x to the 0. You could think of it that way. Or you can just plug infinity in. What's infinity cubed? It's infinity, right? But we know that this is the case because the denominator is higher than the numerator is higher than the denominator in terms of their power, so it will always be infinity. What about the limit as x approaches infinity of 2x minus 1 over x plus 1? Here, because they have the same power, we just look at the ratio of the leading coefficients. We get 2 over 1, which is just 2. So if you have any questions about finding limits at infinity, please shoot me a reminder or ask a question in class.